Hi, here's one of the example problem that I would like to show you uh, in fluid dynamics. It's a very popular problem. So have you ever wondered how airplanes fly and how airplanes get lift, the necessary lift? To understand this, you need to understand the fluid dynamics principle. So mainly Bernoulli's effect, Bernoulli's principle. And the airplane wing gets most of the lift by creating a pressure difference on the top and bottom of the wing as shown in this diagram. Because if you look at the wing design, the wing has a kind of airfoil design, aerodynamic airfoil design, and because of that, when airplane cruises with some speed, the air molecules has to travel at faster speed on the top of the wing, right here, top of the wing compared to the bottom of the wing, and that creates a pressure difference because we know higher velocity, faster velocity means lower pressure, and vice versa. So because of this design, aerodynamic design, the air molecules, your fluid system is air molecules, has to travel faster on the top of the wing as shown in the diagram compared to the bottom of the wing. Bottom of the wing is almost flat, right? So since the air molecule is traveling at faster speed on the top of the wing, it creates a low pressure region here. It's a lower pressure region compared to higher pressure region on the bottom of the wing, and that creates the pressure difference, and that creates the necessary lift, right? And so given the information, let's say that here in this particular problem, this is just an example, this airplane is flying at 200 meters per second. That means the air speed on the bottom of the wing is 200 meters per second, and because of this airfoil design, it says the air molecules are traveling at 240 meters per second on the top of the wing, right? That's the speed difference in speed, and this is the average thickness, and this is the size. Based on that, it's actually what is the net lift force produced on the wing due to this Bernoulli's effect that we just mentioned in the previous video, the previous lecture, right? So to do that, let's first draw a free body diagram on the wing. So I'm gonna first begin with a free body diagram on the wing, right? So we call it something called free body diagram on the wing, right? And in the free body diagram, right, the wing can be simply replaced by a dot, and you have two pressure forces. Remember, pressure is force over area, right? This is from the very beginning of the fluid mechanics. So the pressure force is pressure times area. So it's actually driven by two pressure forces. One is this way, right? Downward pressure forces. Let's call it P2A. And you have a stronger pressure force acting on the top in upward direction from the bottom up, right? Like that. So this is the pressure force, and that's why, so P1, so we call this region as region number 1, the top of the wing as region number 2. So these are the pressure forces acting on the top, right? This is acting on the top of the wing, and P1A is the pressure force acting from the bottom, on the bottom of the wing, right? In positive y direction. This is on the bottom of the wing. And you can clearly see the pressure force acting on the bottom of the wing is stronger than pressure force acting on the top of the wing, because you are creating a lower pressure region on the top, and that creates a net lift, and that's what we're going to calculate, right? So then your main equation is the magnitude of the lift is given by P1A minus P2A, but the area of the wing is common, right? Is same for both, so that's why you can you can simply say P1 minus P2, which is simply the pressure difference, times that's the lift. That's the force of lift produced on the wing, right? And let's call it equation number 1, because to calculate the net lift produced on the wing, first you have to calculate this pressure difference, let's call delta P, because the area of the wing is given. So to calculate this, you have to first find the pressure difference, which we will calculate using the Bernoulli's equation that we mentioned, right? So now using the Bernoulli's equation between region number 1 and region number 2, so I'm going to first write down the Bernoulli's equation. P1 plus 1/2 the density. Now the fluid system here is air. The V1 square plus the density of air, gravity, Y1 is equal to, on the right hand side it will continue, right? So it's P2 and 1/2 the density of air, V2 square plus the density of air, gravity, Y2. That's simply Bernoulli's equation. So our main job is to find the pressure difference P1 minus P2 from this equation, right? So you just need to now play with this Bernoulli's equation, right? So just rearrange that. So I need P1 minus P2, right? So then I can bring this whole thing to the right hand side. So that's going to give me 1/2 density of air, V2 square, minus 1/2 the density of air, V1 square, and plus the density of air, Gy2, minus the density of air, gravity, Y1. So you can do one more thing, one more step to simplify that. So 1/2 the density of air, 1/2 density of air is common, so you can factor that out. So V2 square minus V1 square plus the density of air, gravity is, again, you can factor that out, Y2 minus Y1. So remember, now we are given this velocities V2 and V1. So V2 is the velocity on the top of the wing, which is 240 meters per second, right? V1 is the velocity on the bottom side of the wing, which is 200 meters per second, and everything is given. So density, it says the density of the, it says to use the density of air fluid as 1.29. So let's put all the numbers and let's calculate that. So 1/2 1.29, and the V2 is 240 square minus 200 square. Again, the density of air 1.29, gravity is 9.8, right? And Y2 minus Y1 is simply the thickness, right? This thickness, the average thickness, and it says the average thickness is 10 centimeters, it's 0.1, right? 0.1. Okay, so it has, you can clearly see, it has very little contribution in the pressure difference. So this will give you P1 minus P2, which is the pressure difference it creates, right? And that generates the lift. And I'm gonna now just so that's gonna give me, after calculating, it's gonna give me 11,353 pascals. Remember, it's standard English pascal. Now we're almost done. Then now from equation number 1, the lift, right, produced on the wing is the change in the pressure, which we just found, times the area of the wing. So change in pressure, the difference in pressure is 11,353 pascal, 353, times the area of the wing, let's go back, is 13 by 3, right? 13 times 3 is already in meters square. So this is, here you go, this is the lift produced on the wing, and that's gonna give me a big number, 442777, right? So you can say, and its unit is, so what should be the unit of force? So the standard unit of force is newtons, of course. So you can say is 443, about 443 kilonewtons. So that much lift force will be generated, right, because of this fluid dynamics, this design.